Good evening. From the Gail Lemron Auditorium on the campus of Embry-Riddle, welcome to the Embry-Riddle Speaker Series, presented tonight by the College of Engineering, the Honors Program, and the Speaker Series. This trifecta presentation is the second time that we have done this, and tonight we are very pleased to present Dr. Pat Anderson. He will be doing a discussion that will take the better part of 30 minutes as to the future of urban mobility. And we will do a Q&A section within the body of this program. We thank you for joining us here tonight. To begin the festivities and to open our program, I call upon the Honors Program Chairman, Dr. Jeff Kane, to come and speak to us for a moment. And then he will introduce Dr. Marc Bernier.
Hey, good evening, everyone. As Mark said, it's a triple threat. It's nice to work together with him and with Dr. Mirmurani. Probably 10 or 12 years ago, we began co-sponsoring the Engineers Week keynote address, and so it's become something of a tradition. It got started because the honors program, now in its 16th year, from the very beginning has had probably 60 to 65% of the students in the honors program are in the College of Engineering, quite a few of those in Aerospace Engineering. How many honors program students from AE are there here this evening? Yeah, okay, good. So we enjoy a great partnership. It's good to work together. Our students are involved with so many of the engineering faculty, and we're happy to participate. So with that, I'll hand it over to our Dean of the College of Engineering, Dr. Marc Bernier.
Thank you, Jeff, and good evening, ladies and gentlemen. It's a great pleasure to welcome you all to the 2019 Engineers Week keynote address. I really appreciate everyone taking time and coming to this presentation, and I guarantee you would not be disappointed. We have a great speaker. Before actually talking a little bit about National Engineers Week, I'd like to recognize some of our members of the upper administration of the university who are here tonight. I'm going to start with the university's Senior Vice President for Academic Affairs, Provost and Mrs. Moeller. They're here. Please give them a round of applause. Ms. Ann Botteri, Vice President for Marketing and Communications. Mr. Charlie Savastus, Vice President and General Counsel. And Dr. Randy Howard, Senior Vice President and Chief Financial Officer. Well, thank you very much, everybody. Especially welcome the members of Daytona Beach community. National Engineers Week is always the week in February, which coincides with George Washington's actual birthday. February 22. George Washington actually happens to was a surveyor, but he was recognized as a civil engineer and first American engineer, so hence the coincidence. It is observed by most engineering schools, education and cultural societies, and many corporations and government agencies. The purpose of National Engineers Week is to bring public awareness about what engineers do every day to make life better for all of us, and to call attention to the contributions to society that engineers make. It is also time for engineers to emphasize the importance of learning math, science, and technical skills through community outreach, as our College of Engineering has been doing and will be doing all week long. So I'm supposed to tell you about what engineers do and how they contribute to society every day. I guess I could do that. I've been the dean for a long time. But I prefer that you hear it from the man whose name is quintessentially associated with the marvel of engineering, an aeronautical engineer himself, Neil Armstrong. Let's watch a short video.
I am, and ever will be, a White Sox pocket protector nerdy engineer. Born under the second law of thermodynamics, seeped in the steam tables, in love with free body diagrams, transformed by Laplace and propelled by compressible flow. As an engineer, I take substantial amount of pride in the accomplishments of my profession. Science is about what is, engineering is about what can be. Engineers' entire existence is dedicated to doing things better and more efficiently. It is a profession which leaves its imprint on our society in countless ways. A century ago, the world really needed improvements in quality of life, health, mobility, and living standards. At that time, life was a constant struggle. The 20th was a century often punctuated with the terror of war and darkened with societal struggles to overcome injustice. But the 20th was also the first century in which technology enabled the tenets and the images of those traumas to reach across the world and touch people in ways that were previously unimagined. Engineering helped create a world in which no injustice could be hidden. Many will look back to see how we have changed and what we have accomplished. The future's a bit foggy, but it's not unreasonable to suggest that the 21st century will enjoy a rate of progress not unlike the 20th. It's something to hope for.
Now, it is my great pleasure to introduce our keynote speaker, my colleague and good friend, another great aeronautical engineer, Dr. Pat Anderson. Dr. Anderson works in the area of new technologies, including vehicle concepts, alternative aircraft propulsion, advanced flight controls, learn to fly, and novel certification strategies. He was the advisor for the world's first piston gas electric hybrid aircraft, the Eco Eagle, designed by students in this university and flown in NASA Green Flight Challenge. In 2012, he was awarded Florida State University Professor of the Year by the Carnegie Foundation. He has been the recipient of Embry-Riddle's Researcher of the Year and the Lindbergh Foundation's Electric Propulsion Innovation Prize. Dr. Anderson has advanced degrees in mechanical and aerospace engineering and holds an airline transport pilot rating, certified flight instructor rating for airplanes land and sea, instrument airplanes, multi-engine, glider and helicopters, and an airframe and power plant mechanics rating with inspection authorization. Dr. Anderson is currently a professor of aerospace engineering and the director of Eagle Flight Research Center at Embry-Riddle Aeronautical University. Ladies and gentlemen, please help me welcoming Pat Anderson.
Thanks, Todd. Thanks for joining us in this new exciting area. So I'm going to take us through a little adventure here, starting where we're at today, maybe even a little further back, and see how some of the things we've seen in movies actually foreshadow what is about to happen. So this is the age of urban air mobility, which is the follow-on to things like Uber. We've sort of seen this before. This was the year I was born, 1968, with Captain Kirk, and this was supposed to be 2150 when the Starship Enterprise showed up and all this technology arrived, but it arrived a little sooner. William Shatner looks a little worse for the wear, but there's that. Here's the Spirit of St. Louis. This was 1927, and unfortunately, the way this is played out, that's a 2019 Cessna Caravan right there. And unfortunately, they don't look too different. The good news is, I think that's about to change. So airplanes for about the past 115 years have looked the same. And now we're about to see a rapid change in that. So you could say Avatar there, 2154. I don't think we're going to have to wait till 2154. I think in the next 5 to 10 years, we're going to see vehicles that look like this, that transform what airplanes look like into the next age of airplanes in urban air mobility. And that's going to require us to think a little bit different. So I have Think Different Part 1. We started down this path of how is this going to happen? How is this going to unfold? And the first thing that we saw was electric airplane propulsion. And so as we looked at that, we looked at the classical aircraft engine. And when we go to school here in aerospace engineering, lots of times what we do is we say, let's put the control volume around this, and let's look at that engine. Let's try and make the fuel flow of that engine less. But we might have missed the point. Maybe we have to expand that control volume out. Maybe we have to look at the whole airplane. Well, when we get to aircraft design, we look at that too. Maybe we have to fold more than just the airplane in there. Maybe we have to fold in where the energy came from, where the emissions occurred. And so maybe when we put gas in this airplane, we have to consider the petroleum plant where it came from. We might have to consider the vehicle that brought it here. Now we have electric airplanes. The airplane we competed against in NASA's Green Flight Challenge was a Pipistrel fully electric airplane. And I have a Bart Simpson nuclear power plant there. But actually in Santa Rosa, California, the energy for that airplane did actually come from geothermal. So the actual greenhouse gas and other emissions were nearly zero in that. And so this has made us think a little bit. What if it happens to come from coal? So in fact, we've met up with the Argonne National Lab trying to learn what is the wells to wings sort of transformation of energy as we use it, and how can we use that in our design process. If you look at West Virginia up here, that black circle indicates that that is coal. So the interesting thing that they say is a Prius that's being driven in West Virginia may make more emissions than a Suburban driven on gas because it's coming from coal. If you look down here in Florida, we're in the middle, we're using natural gas. If you look up here in Washington State, that blue indicates mostly hydroelectric production of power, and that has almost no emissions. So we're now starting to fold this into our idea of aircraft design and thought about using electric and hybrid propulsion as we moved on. And so how do we evaluate good? Maybe we have to expand that out all the way to looking at the entire world as our control volume. And of course, this is round peg, square hole, typical, so let's do this. But propulsion enables aircraft design. So we're now in the third generation of aircraft design. We first had piston-driven airplanes, and this is a kind of a funny airplane. This looks a whole lot like a piston-driven airplane. That's a XP-59, the first jet-engined airplane of the US. And it looks so much like a piston airplane because we didn't know what to do with a jet engine. We took a propeller out, and we put a jet engine in. And in fact, when it was out at Muroc Airfield, they stuck a plywood propeller on it so the Nazis couldn't figure out that we actually had invented a jet engine airplane. And this was very believable back then because it actually did look like a piston-driven airplane. But that's not really what took advantage of the jet engine. It was 15 to 20 years later where we came up with the Century series airplanes, and we said, that's what you do with a jet engine, not the first one. And so now we're at this point where we're thinking, here's an electric motor. So this is one that we have over in the Eagle Flight Research Center. That's a 100 horsepower electric motor. It weighs 67 pounds. And we thought, well, we pull the recip engine out of our airplane and we stuff that in and we have an electric airplane. And guess what? We missed it again. That's not the thing that electric propulsion enables. That's the thing that electric propulsion enables. So what is urban air mobility? Urban air mobility is the idea that you can have a practical flying machine that can replace the mission of a car or a van in a city environment. And this is really radically different from airplanes that we normally see because almost everything we're doing in normal aircraft design class is either to minimize emissions, fuel flow, or maximize range and endurance. And this is the opposite of that. It has to only go a little way. And so this flying machine, what does it look like? Well, it's a helicopter-like aircraft that uses electrified propulsion. And that's really important. It enables, the electrified propulsion is what enables this, and it enables it to fly as quiet as a car or truck, be so redundant that it can fly over cities. So this is orders of magnitude safer than a helicopter, allows autonomy like AI and other types of autonomous operation, and beats a surface vehicle in speed, safety, efficiency, or all of the above. And so what are we trying to do with this? We're trying to replace that Uber on the left going 30 miles down in South Florida that might be going 16 miles per hour average speed during that course with a vehicle that looks somewhat like a helicopter that has almost no variability in the speed that it takes to get there. So that's the mission there. What urban air mobility is not, I always got to put this up here, right? So you've seen the James Bond movie where the car comes out of the garage. Well, we've been trying to make these for a long time. This is an owner-operator. This is the idea that you could own a flying car and pull it out of your garage and take off in your driveway. That is not what this is. Maybe someday down the road that's what it'll be. This is literally taking surface urban air mobility like Lyft or Uber and replacing that car with a vehicle that can do the same mission within a city. So we're selling tickets. The vehicle is going to fly 20 hours a day. That amortizes the cost of the vehicle. What it is not is a long-range vehicle, and it may not even be more efficient than a helicopter or an airplane, but we'll talk about that in a second. I'd like to show you Uber's idea of what this is. So that's Uber's idea of what's going to go on, but they're really smart. They're great marketers because they don't plan on building any of these, right? Just like the cars, they don't build the cars. So they've put this out and said, you go build them and we'll make money off of you having done that, right? But it has really spurred on a lot of people to come into this area. And the question I always get is, why not a helicopter? So why not a helicopter? Oh, you're just stretching? Go ahead. Slow? That could be one thing. Safety issues? Safety is actually an issue. With the numbers they want to deploy, you'd on average have a helicopter falling in a city once a day.
Pretty loud.
Really? That's it. So that's my friend Eric Lindbergh going out for a backcountry ski, and helicopters are loud. They're very efficient vehicles. We've spent 80 years developing those, and I'll come back to this in a second, but they're loud. So we sort of missed the mark on Think Different 1, although it really spurred us to Think Different 2. And Think Different 2 is bringing this vehicle in, and you got to think, do I compare it to this? Well, you can think noise was said, safety. These are orders of magnitude safer potentially because of their redundancy. You can think emissions. Helicopters are amazingly efficient vehicles, but I want to put 200,000 of them over cities. So is that going to go over well? Maybe, maybe not. It's not really the helicopter, though, that I'm competing against. What am I competing against in this? That's what I'm competing against. And so when we go to school in aerospace engineering, we don't compare our vehicle to a car. And so we have to expand that control volume out even further, because we may not be competing against a helicopter when I look at designing this. I may be competing against that. And I might not have the ability to fly a helicopter in there because it's too noisy. So having a quiet vehicle is an enabling technology. Having it safer than a helicopter is an enabling technology. So we've had to think different about this. So what is the enabling climate that is allowing this? One is the market. And so one of the things that Uber has that everybody that has a cell phone in their pocket knows is that they're tracking what we do. So they know exactly how many people go from JFK to downtown Manhattan. They know how fast you get there. They know how much you're willing to pay. They know how much you're willing to pay more if you get there faster. And so this is a really simple business plan. If you amortize how often the vehicle flies, you can figure out how many vehicles, what the cost of the vehicle would be. And what you end up with is it doesn't cost any more than a regular Uber to do this. And so what we see is a large number of, especially Silicon Valley, wealthy people, a lot of the people that are not getting into the commercial space race are investing significant amounts of money in this, on the orders of hundreds of millions of dollars. The technology is here right now. There's electric propulsion, hybrid drivetrains, autonomy, and artificial intelligence and modern flight controls allowing this. And the third part of this stool is the regulatory environment. If you would have asked me 5 years ago, I would have said it's all there right now, but there's no way the FAA is going to let us do this. And here at Embry-Riddle 2 years ago, a committee of ASTM, GAMA, and the FAA sat down and they changed FAR Part 23 to now allow this type of technology. So I'll say a little bit about that. 2 years ago, FAR Part 23, which is a certification of small airplanes, was 377 prescriptive regulations. I always joke, we certified the first diesel engine here, and the FARs said at that time, and the FARs are law, it said every engine must have 2 magnetos. And we're like, well, that's just a joke, right, for a diesel engine? Well, no, it's a law. So the first thing we had to do to certify it was get rid of that law. So anyway, they've changed those. And what they've done is they've changed it so that it's not prescriptive. What it says is the vehicle must be safe. It no longer says it must have 2 magnetos. It doesn't tell you how to do it. It just specifies how safe it needs to be. And then a consensus group of knowledgeable people can vote on, here's some new technology. Do you believe that works? They all put their hand up, and if they all agree, the answer is yes, and you're allowed to certify in that way. And so the regulatory environment has changed drastically. And again, I'd like to pat Embry-Riddle on the back because most of that happened here at the university. The market, as I said, you can end up with vehicles that go 5 to 10 times faster at the same cost as premium ground transportation. If you look at an Uber in South Florida, you might want to go 30 miles. You might average 16 miles an hour, which is almost 2 hours. And the variability in that is depending on if there's accidents, traffic, or whatever. So you may go at 60 miles an hour one day and 5 miles an hour the next. Whereas a personal air vehicle is pretty assured to go about 150 miles an hour, 12 minutes, no variability in all this. So the business model, again, is there. This is a picture of Dallas. There are cities right now that are vying for heliports, so this is intercity travel, and there is some infrastructure that has to be stood up with this. So you're going to end up with helipads, places at airports where these vehicles can land. Another great talk about if these are fully electric, how do you get the electricity up to the pad? We're talking about a whole bunch of electricity, or if it's a hybrid, getting the gas there, so putting the infrastructure in, and people like Argonne National Lab are starting to look into this. And so to give you an idea of what they find at the end of these spreadsheets is that right now the average speed in the city is about 20 miles an hour. It might be good one day, bad the next day, lots of variability. Uber is pointing out, and Lyft is pointing out, that this is $276 billion market in on-demand mobility, and they think that they can slice off 30 billion of that in aircraft, which has a mature size of 60,000 to 200,000 aircraft, which, by the way, would double the number of aircraft on the planet if you're counting. What technologies enable this? Well, distributed propulsion is one. Who said safety? Somebody said safety out there. So here I have 8 different propulsion systems, and I could probably lose 3 of these and still fly. So that's one side of it. Over here I have 3 different ways to make the electricity. Here I have 2 generators, 2 different piston engines driving a generator, and then I have a battery, and any one of these 3 can keep this vehicle flying. So now I have 3 sources of power. And what you find out is I can hit that airline like 10 to the minus 9 or 1 in a billion chance that it would fail. Driving a lot of that is battery technology, propulsive batteries, which we're working on over at the Eagle Flight Research Center. There's an enormous design space with this. I'd love to see what the next design book looks like. I mean, it's going to be something this high. It won't, because it'll be on a computer at this point. But it's a gigantic design space, because we go all the way from classical gas turbines to electric motors with hybrids sitting in the middle, parallel, serial, air charge, no air charge, ground charge. The number of ways you can iterate on this is huge, and we're trying to work ourselves through that space. Here's a typical gas engine. I'm going to talk a little bit technical now just to give you some little nuggets of why this all works. Over here, if I look at a typical gas engine, the torque is tied directly to speed or RPM of the engine. So if you tell me speed, I tell you what torque it makes. In an electric engine, that's a little bit different. So up here, I have, this is a curve for this engine right here, this electric motor. And what this says is this is the efficiency. And basically what this means is I can pick any speed and make any torque. So they're completely decoupled. And so what that means is I can generate very high torque at low RPMs. I can pick to be wherever I want on this map, and that'll come into play here in a second. What that allows us to do is turn our props and rotors very slowly. So I don't know if you know this, but the speed of a rotor or something making thrust, how fast that turns, really has a lot to do with how much noise it makes. And so the slower I can make that, the quieter the vehicle is going to be. And so we've ended up using electric motors to operate it at low RPMs using high torque that electric motors can make. In doing that, we've built new prop rotors that take this technology into account. And so if I combine all of these things, what I end up with is the efficiency of my electric motor. I can figure out what the rotor or propeller is going to do, map over that. Once I map over that, I can figure out the total efficiency of the propulsion system, which ends up being in the 80% for an electric airplane, as opposed to 30% for a gas-powered airplane. And then put in a line of constant thrust. This, I can operate the airplane anywhere on here and grab the noise that it makes and overlay that on here. There'll be a test later on this, so I hope you're taking notes. And what I find out after doing all that is that there's a position of maximum efficiency, which is where we always fly to the past 115 years. This is where we fly. But we find with an electric motor and a specialty rotor, we can slide along this line the passengers would never know, and we trade propulsive efficiency, 64%, for 30-some-odd% propulsive efficiency, but we peel off 15 dBA of noise, which is the invention of Blue Thunder. How many people remember Blue Thunder? I'm getting very old, right? Roy Schneider, Blue Thunder, silent helicopter. This is the derivation of the silent helicopter. And so electric propulsion enables this. We also look at artificial intelligence. We're starting to get into rudimentary learn to fly. So vehicles that are complex to control, instead of using textbooks to figure it out, we can have it learn like a child learns to fly. And so on the left-hand side, you see the child. This is the same airframe as this. This is a year later after this vehicle learned basically on its own, well, with some help, to fly. You see the amazing difference between those two things there. There are some bumps in the road in this. There's some scaling laws. There are some physical barriers that are interesting to look at. One of them is that a lot of people use fixed pitch blades because this is really looking a lot like the drone market. So you guys have all seen the explosion in the drone market, multicopters. Well, the way those things control their attitude of the vehicle is by changing RPM on fixed pitch blades. Unfortunately, as those blades grow, the thrust-to-weight ratio goes down because the electric motor gets heavier faster than it makes thrust, which is kind of complicated to explain, but there's that curve. And what I'm trying to say here is that we have a lot of people, I'm sort of the gatekeeper of this. I get a lot of folks that come in and they say, well, I've got this and I'm going to scale it up to the Avengers aircraft carrier. Okay? And in fact, there's 5 that I can count of that have convinced people in multi-billion-dollar deals that they can actually do that. And the answer is they can't because of this scaling law. Is there a way around this? So you can't do this. But the good news is if you use a rotor blade like a helicopter, this is scalable. The bad news is that the people doing this in their backyard and their garages don't have the ability to make helicopter rotors. So it gets more complicated. The other one is hybrid versus fully electric. And I'm going to give you a little automotive analogy. Do airplanes and autos track each other? Because a lot of people think they do. We're going from gas to hybrid to electric vehicles in cars. And the end goal is sort of fully electric. So I'm going to ask the question, why do we have hybrid cars right now? Range. I heard some others, but I'm going to stick with range, right? No, the answer is not range, and that's the 90 percentile answer that I get. And you've got a Tesla, right? So if I put another 85 kilowatt battery pack in the back of that Tesla, do you still think it'd go pretty fast? Probably. So at that point, when I put a second battery in it, it would have the range of any other car. But the reason that they don't do that is it's price. You would have a $140,000 car at that point, and guess what? They wouldn't sell enough of them to make it worth the while. So in automotive, the limitation is bucks. Everything that goes into a car has to be as inexpensive as possible. And so it's really interesting because the government, the Congress has said to Argonne National Labs and some of the other labs, we would like you to make vehicle batteries better. And by vehicle, they defined it as car and not airplane. When I went to school, I thought vehicle included airplane. So that's Congress's definition there. And better meant cheaper. And so you see them putting billions of dollars in, and this is what a capacity of batteries costs, and it is dropping like a stone. And that pink area there is $150 per kilowatt hour of battery storage. And at that point, an electric powertrain is cheaper than a gas powertrain, and guess what? We all switch to electric. So the end game is fully electric, and the reason that we're not there is cost. On the other hand, for an airplane, what is important is weight. So this is tracking the specific energy, which is how much energy per weight I can carry. And I think a lot of people just thought, well, we'll just wait around for batteries to get better, and that'll happen in 3 or 4 years, just like computers march on at a very fast pace. And Don Hillebrand from the Argonne National Lab said, well, I hate to tell you, it's 3 to 5% per year. And it's been that way for 40 years over multiple chemistries. And so you see, if you start projecting this out, what we end up with, it's kind of a long explanation, but batteries just don't cut it. Although they help this whole thing, they help with the electrified propulsion. But pure batteries aren't there yet. And even if there's a Nobel Prize winning change in chemistry, it's not going to be in an airplane tomorrow because of safety concerns. So the good news is that there's another way out of that, which is not using fully electric, but the mature version being hybrid. So, I drew out for automotive that we started with gas, we went to hybrid, and then electric. But in fact, what is important in the automotive industry is cost is king. Weight, they don't much care about. Volume is sort of important. In the aerospace industry, it's actually weight, volume a little bit, and we could care less about cost. I wish that weren't the case because I own an airplane. But we appear not to care about cost in aerospace. And so really this switches around. It doesn't go gas, hybrid, electric. It switches. We've seen some smaller airplanes that are electric, but the mature area, at least for a long time, until batteries get about 20 times better, is hybrid. And so this has been really interesting to watch the capital investment on this, because if you build a subscale version of new technology on an airplane, you're pretty much assured if you saw a version of that fly that was smaller, you could scale it up. And in fact, most scaling laws in aviation are such that it gets better. And so there's some urban air mobility folks that had small scale flying versions, and they hooked people hook, line, and sinker on investing. But what they had was the golf cart, the fully electric, the simple one. And they had to fix pitch rotor blades at very small scale, which doesn't scale. And so what they had was a very simple version, and that was sort of like capital investment one fail. And so now they're looking at much more complex vehicles that are hybrid with helicopter rotor blades. Now, let me stop for a second. I see a lot of the younger folks in here. Let me say something. It's your turn. You're about to change the world. Airplanes are not going to look like they've looked like for the past 115 years. They are about to make a right 90-degree turn in all of this. I got to tell you, I'm going to say that this is some unknown Penn State professor. When I got out of school, they said, you better learn structures fast because we know everything there is to know about aerodynamics. And the funny thing was, they were right when the wind blew right at the nose of a stable airplane. And if you moved it up a little, we were okay. Moved it down a little bit, we were okay. Moved it here, okay. We're not doing that anymore. The wind's coming from here, and here, and here, and back there. Guess what? I'm back into a job, because we don't know what the aerodynamics happens from those particular wind angles. And the vehicle probably looks like that. So why did I say this was a golden age, or the age of urban air mobility? You know, the golden age of barnstorming. This is when the Wright brothers, Lindbergh, and those folks, there was a very steep learning curve. And then recip engines kind of lean over, and we gain a couple of % every year. Then there was a golden age of jets. We screwed up a little bit in the beginning and had a little dip, but then it picked up. And again, jets are sort of leaning over, and we know about all there is to know about jets. Well, guess what? We're in the third hump. There it is. Electrified propulsion is going to enable all of these things to happen. So how many UAM companies, urban air mobility companies, do you think are out there? Well, if this were 4 years ago, it would be that white blank piece of paper. Is that all of them? Is that all of them? No. That was 2 weeks ago. I bet there's another 20 more on there. So this is that golden age, and there's some very serious organizations up there. I'll say, when was the last time you saw Boeing and Airbus making commercial 2-seat aircraft? 140 last week. Now I'll go back to my friend Eric Lindbergh with my parting comments that the enabling technology here is safety and noise. And helicopters are wonderful vehicles, but they're noisy. There's Charles Lindbergh's grandson.
Great job. Great job, Dr. Anderson. I was thinking about so many different things you had mentioned when we had lunch earlier today. If we have that many vehicles, as you stated in the presentation tonight, what kind of noise are the carbon footprint people going to make when you get all those vehicles out there? Will they have room to argue against it because you're going to have that many vehicles?
Well, it's a really interesting dichotomy, because if you compare it to a helicopter, you'll probably lose. But the helicopter can't fly that mission, and you're not replacing something that a helicopter does. You're looking at that car, And if the car is just going straight and doesn't hit traffic, you're probably in trouble. But when you get into a city landscape and there is traffic, and you start comparing that in-traffic emissions, gas and carbon and CO2 to the mission of this vehicle, it may actually win in that particular case. And so we know the people are going to move back and forth. So are you replacing that car with something that's better than the car? And the answer is yes.
Will weather be a factor if we have a sudden change in weather and we have a fleet that's moving in the city, or do they operate the same way that airplanes would? They just don't fly if the weather is very inclement.
Well, that's another great question. These vehicles are only made to go about 25 miles, and so hopefully there's not very many surprises. The difference with airplanes that are out there today, like a 747 or something, it's taking off, it's going to fly 12 hours and go somewhere, and in that time you could get surprised. You could show up at the destination and have bad weather, and you're probably going to have to land there. The early deployment of these are, they've looked at, for example, New York, and when is there icing in New York, and they say that's only parts of 3 days a year that really happens. So the early deployment will probably stay away from really bad weather.
I don't want to take you too far into the financing, but people in our audience know that Votran is government supported, in part underwriting that lowers the cost of how much it takes to do a ride. Trains are in the same situation. This type of technology, at least out of the gate, sounds like it might be so expensive that it may have to be underwritten by government. Do you anticipate that?
Well, I look at it more like commercial space. This is the first time in this sector of aerospace we've seen a huge influx of capital investment. So the business model in this is such that I don't think the standing up of the technology is going to require government intervention. So I'm not sure that the government will have to support the lower layer of it. If you look now, it's just an absolutely astounding amount of capital going in. Just in the public domain, you can see over $1 billion of capital flowing into the R&D of this in the past year, and that means behind the scenes it's much greater number than that.
One of the questions that we had earlier today was, does everybody want to get on board to do this? Are there municipalities that say, no, we don't want urban air mobility? And you said there are cities competing. You do have some saying no, but others are competing.
Yeah, you run the whole gamut. There are some cities that say, well, I don't want these things to rain down on our head, and nobody does, but that turns them off. There are other cities that embrace this as the new technology, and they want to be part of that new technology and part of the emerging market to show how we can put these vertiports in, how to put the infrastructure in, how to reduce the congestion in their city so their city is a nicer environment to move back and forth. So Dallas and some other cities have actually partnered with Uber and others to start putting the infrastructure in for these vehicles.
Do you envision that either the Boeings, those who manufacture aircraft, or the auto industry will look to move to this type of technology to save them?
Well, absolutely. If you look on that list, if I were to go back, you'd see both Boeing and Airbus. There's numerous ones up there. The one that comes to mind right off the top of my head is Aerospace X, which is right out of Detroit, and it's a bunch of the auto manufacturers that are standing that particular one up. So it's not just Silicon Valley people, it's not just backyard, garage people. The big boys have done the spreadsheets too, and they see this coming.
In your briefing to us earlier today, you mentioned about Europe. They seem to be a little more flexible. They're lowering some of the restrictions. We had a lot of restrictions here. Did I hear right that we got to really watch Europe because they may jump in before us?
Well, it was really interesting. GAMA, which is the General Aviation Manufacturers Association, which helps move regulatory stuff forward in the U.S., they sort of pitted our FAA against Europe. Europe was easing their ability to certify things, and they said, well, if you don't keep up, all the innovation is going to flow over into Europe, and they're going to be able to fly these things, and we won't. And so that really accelerated the FAA in changing over to what I was talking about before, which is a consensus standards method of certifying these vehicles.
The presentation, I believe it was Uber that you had, very, very attractive. And you think about people getting into a building, going to a floor in which Uber would be. Would there be a limit? Is the conception that you would have only so many vehicles per port to take off? Because otherwise it get in each other's way?
Well, this gets into a really interesting area. You know, we've talked about UAVs for 10 or 15 years, and there's been all this investigation into how to move that traffic around. NASA has stood up a thing called UAM, which is UAV Air Traffic Management, which would allow these UAVs to self-separate. And the interesting thing now is this is completely merged. So with the technology we have now, it doesn't matter if it's manned or unmanned, urban air mobility or cargo. You can have an unmanned vehicle where the cargo is people. And so the good news is that all these UAV technologies in air traffic management and the sorting out of who lands on the pad has been thought about for 15 years by NASA and other folks for the application of UAVs.
Do the Russians and the Chinese have interest in this so far, or are they not in it?
I haven't seen any Russian vehicles. The Chinese are full into electric. So E-Spider and many of the early, probably half the early electric aircraft were Chinese built. There's vehicles called E-Hang, which are meant as urban air mobilities that have shown up at the US auto shows as demonstrators. They have purchased some of the US companies that are working in this space. Terrafugia, for one, which was stood up by some MIT graduates, has been bought by Chinese companies. So they're very interested in this space.
We're going to take questions from our students here in the audience. If you want to come right down to the microphones, you can ask your questions now for Dr. Anderson. If you come right up, we'll get you in the loop. Before we go to the audience, though, I wanted to ask, I know we're still very much in the creation and the research part of this. Is there any envisioned amount of time that these vehicles may have in terms of a life? Are they thinking because of the fact that they're hybrids, they have a long life? Any idea of how long they would last?
Yeah, it's really interesting. You know, nowadays in airplanes are unlike cars. We mandate that they be taken apart and fixed every once in a while. Engines come apart, and we do what's called TBO, a time before overhaul on those. In these vehicles, the interesting thing is what'll be overhauled is battery packs. And so if you're looking at what market to get into that covers all of these, overhauling the batteries is the interesting thing, because the life of a battery decays as time goes along. And so there will be a life limit on that, but like regular airplanes that live almost forever, we'll just continually replace those or refurbish those as the vehicle goes along. But right now, batteries are such that that'll happen quite often.
Did you say earlier today that the FAA, to get around the, I think it is 23, if it could go up at a certain distance with propellers, it would be okay?
Yeah, well, one of the interesting things, and this gets into the details of the certification, but the helicopter certification is Part 27, and that's not consensus standard. It's still the old prescriptive way. And I've been politicking, and Gamma has been politicking on Capitol Hill to determine that if it's under wing, in other words, if it flies with wing lift for a certain period of time, that it falls in this consensus standard Part 23, which is deemed to be easier. That's really good news, except for the direct lift folks like Volocopter and so forth. They're going to fall squarely in the 27 and have to meet all the old helicopter rules, which probably right now is nearly impossible.
For Dr. Pat Anderson, let's start interweaving questions. If you'd step right up to the microphone, and your name, please, and your year of study here at Embry-Riddle. Your question for Dr. Anderson.
Oh, sure. My name is Miles Osborne. I'm a freshman here at Embry-Riddle studying Aerospace Engineering. My question is, watching the trailer for Uber Air, I saw that this was kind of around large cities or densely populated areas. So I guess maybe like how exactly is this going to fold out on a larger scope? Is it just limited to like these large cities with buildings or space for mobile airport hubs? Or is this going to be also available to like less populated areas, so smaller communities and whatnot?
Well, that's a great question, and that is, in my opinion, the long pole in the tent is because these are very short-range vehicles, and so the actual business plan only occurs in the city. So if you're the FAA, you have to think about what is the control to entry into service. It's not to let 10,000 of them start flying tomorrow over your head, but the business model doesn't work in an urban area. So how do you transition that area? So the answer is no, it doesn't really make financial sense in an urban area, but you may be forced to do an uneconomical startup in an area like that to prove the safety of the vehicle.
We'll move to my right. And your question now for Dr. Anderson.
Right. My name is Cameron LaCourse. I am a sophomore in aeronautical engineering here at Riddle. I had a bit of an idea that that has shown up a couple times in military history. I know that you mentioned that electrical power being held on an aircraft is a bit of an issue because of batteries and weight and all those, and the amount of energy it can hold. But there have been a couple of instances where people have attempted to implement electrical power generation from an exterior on an aircraft. Starting in late World War II, the Nazis attempting to fend off the bomber waves coming in to take out their factories and cities. They equipped their rocket interceptor, the Me-163, with a nose propeller to generate electricity as it flew through the air. Later in Vietnam, this was used in the Su-16 gun pod attached to the F-4 Phantom, where it had a little fan that would pop out into the slipstream around the aircraft to power the gun pod. Do you think it would be possible to use modern technology and efficiency and improvements to create an onboard electrical generation system to supplement the battery power usage on a plane?
Did you get all that, Dr.
Yeah,
Anderson?
I did. So it's a little bit of a perpetual motion machine. It's extracting energy from the air to put it back into the air. So that doesn't really work. There are some times where, a lot of this makes sense on a ground vehicle because you have regenerative properties when you brake. And so there would be some advantages to do that. If you had to decrease the performance of the aircraft, you could pull energy out of the air and put it back into the battery. My hope is that our air traffic management system gets good enough that nobody's being told to be inefficient intentionally. So anytime you would see spoilers go up on an airliner, that would actually work. I hope as air traffic gets more efficient, we wouldn't be doing things like putting spoilers up.
Thank you. Over here now, your question for Dr. Anderson.
I'm Doug Denny. I'm an aeronautical sciences student, and I'm a freshman. So I had a question regarding the uses of pilots in this new invention. Like, how long do you think pilots will actually be flying these, if they will be flying them at all? Or will they just be AI, just like the ones that are being tested at Riddle?
Well, they're definitely targeting these vehicles to be fully autonomous. How long that will take is certainly everybody's question. We wrestle with those. We had a meeting here in December of last year talking fully about autonomy. The FAA did not embrace this at first, but the advent of hybrid and electric propulsion has kind of been a Trojan horse to flight controls. They really did not want to embrace full fly-by-wire in light airplanes. And it makes no sense to take a cable and run a cable to an electric motor, right? And so in that, by its very nature, electric propulsion has computer algorithms and that stuff. They're more embracing of autonomy. And I'm dancing around your question because I really think that this is going to play out on the ground first. Airplanes and these vehicles are actually easier to make fully autonomous than a car. There's less things to hit. We have better regulations on the technology. I think if surface autonomy is embraced and that doesn't get screwed up, then they will embrace this in the air and you'll see it happen quickly. If you see automotive accidents quite frequently, I think we're all going to be hesitant in embracing automation in both the ground and the air.
I want to follow up on something you just spoke of. In the news this week was reported once again that Walmart will be hiring a record number of truck drivers, and they'll be paying them $90,000. But that's a short lifespan, because I have to believe that this type of technology will be used to deliver their goods, will it not? And will Walmart possibly get into the bidding?
So certainly, we're talking about moving people here, but in reality, the first thing they'll move is boxes. And so, yes, they're absolutely talking about using urban air mobility as, the UPS truck that goes through the cities. Now, the good news for the truck folks is that, again, this is not envisioned as city-to-city stuff. That's actually a harder problem. The inner-city stuff is a problem that we can solve with current technology.
And didn't you say inside of 5 years we could see the in-city?
Yeah, we're looking at that.
Over here for Dr. Anderson.
Hello, I'm Victoria Cristiano. I'm a senior-ish in aerospace engineering here. So my question is about So I've learned of times where perceived public safety by the general public and maybe not the aviation community has kind of thwarted some technology development, like for example with unducted jet engines. Do you think that'll play a role in the progress of urban air mobility vehicles?
Yeah, it absolutely has to be much safer. It's kind of funny, we had this discussion in my graduate class yesterday. They said, well, helicopters are really safe. And I went to the NTSB site and I just typed in Robinson, which is a make of helicopters, and there's 1,400 accidents that came up. And if we're trying to deploy these flying 10 hours a day at 100,000 vehicles in cities, that would be multiple vehicles crashing per day, which would be completely unacceptable. Now, the good news is you saw all those independent threads on both the production of thrust and the generation of electricity, and that redundancy stands out in a fault tree analysis as OR statements, and it takes the reliability of the vehicle way up. So you're probably looking at airline type safety requirements. 1 in a billion chance of failure is what you're going to need if they're flying the hours they plan on flying. From an unducted fan standpoint, I think they're going to keep the fans out of the way or make it so you can't walk into them. Aerodynamically at subsonic speeds, it's kind of a loser, so I don't think they'll put ducted fans on these.
Do you need municipal air traffic controllers to do this?
Well, that's another thing that's going to, again, to autonomous function and AI, this self-regulating systems that talk to each other. And this is this idea that NASA has proposed of UAM, this independent sort of system. So it may not be ground controllers. These are also thought of as being very low altitude. So we're talking about 500 feet. We're talking about lots of vehicles. So they're basically going to have to communicate with each other and self-separate and sequence as they go through this.
Let's come over here and your question for Dr. Anderson.
Hi, my name is Drew Policelli. I'm a first-year aerospace engineering student here at Riddle. My question was, what kind of impact do you think that this technology will have on the broader general aviation landscape outside of cities?
I think it's going to have a huge impact. This is step one. The short range, it's great because electric propulsion is right now immature from the battery technology standpoint. So it's great that there is a application that is low range. After that, what we're going to see is what we call thin haul commuters. So as the batteries develop, you'll start to see airplanes that I would call more normal looking that end up being battery powered. And then we're going to really start hitting the green nature of this technology where we can really lower emissions, fossil fuel usage, CO2. And the good news about it is it'll also affect the direct operating cost because an electrically propulsed airplane will cost 25% of one that is run on fossil fuels. So there'll be incentive by the people operating it. It won't just be an incentive to be quote unquote green. There'll actually be a financial incentive to switch to this. So as the batteries progress on, we get good with this technology, that'll start deploying to longer and longer range vehicles until finally it's up to the big airlines. That's probably out 50, 75 years, but I think you'll see thin haul inside of 25 years. You see some right now out there trying to do this. Zunum Aviation, which is at our Prescott campus, those companies are working on that technology right now, so it's going to keep marching on.
Dr. Anderson, I know that it's early, but is the National Transportation Safety Board doing a weigh-in at this point?
I think they're watching these groups of consensus standards to see what you do with a battery. I'll give a battery example. The previous way airplanes looked at batteries was you made a coffin. So you put a battery in this box and there was no way for it to explode and get out of the box. Well, now the batteries are so powerful, there's no box that's going to contain this. So if you make a coffin for it, you've just made a bomb basically instead of a box to hold your battery. So now there's ways to exhaust gas if this thing starts having a bad chemical reaction. And so the NTSB is watching all this as it plays out. But it's really novel technology, and they have a hard time keeping up with industry. And so they're really bringing in industry and academia to say, what do you think of this? Is this really the way this is going to play out?
To my right now, your question for Dr. Anderson.
Hello, I'm Nicolas Albrecht, also a freshman aerospace engineer here at Riddle, and I was going to ask about something concerning the logistical implementation of this, because as we saw in the Uber trailer, they had this thing where you went up on the skyscraper and you had the separate floor for Uber-related things, and it was basically like an airport terminal. I would think there would have to be some potential collaboration with in-city businesses or such to use the top floor of their buildings for that. How do you see the potential for the companies that Uber kind of outsources this to collaborate with any kind of business that has a space available in the city?
Well, that's a great point too. It flashed by, so I'm sure nobody saw it. But when that Uber commercial ended at the end, there weren't just airframe manufacturers. There was SharePoint, which is a charging company. So the infrastructure has not gone unseen. And so right now there are a lot of committees standing up to do things like, what does a plug look like? Right now in the automotive industry, there's like 6 different plugs. And it's making people insane, right? Because you can show up and your plug doesn't fit in your car. And so they saw that go wrong, especially at Argonne National Lab, which is one of the national labs that really look at these things, and they are standing up standards and infrastructure. It's a really interesting because there are people that are hesitant and people that want to run forward, because if you freeze the first plug and say everybody has to use it, the plug might really suck. If you allow it to innovate for a while, you might come up with a better plug, but if you let it go too long, you end up with 5 of them, and then you've got a problem again. So there's a lengthy discussion of where do you stop that process and say, okay, this is really good, and we're going to freeze this and make everybody use this. Same thing goes for how do you get the electricity. I mean, we're talking about megawatts of power going to the top of these vertiports, and that's not a trivial concern at all. And so there are lots of people looking, and again, it's an entrepreneurial thing. They see that this business model exists, and so you see all the tier 2 folks are standing up saying, well, I can be the person that supplies this for that mission.
Over here, your question for Dr. Anderson.
Good evening, my name is Beckett. I did bachelor's here in Aerospace Engineering and then doing now PhD in engineering physics. So the question is about this connection with the airport again terminal. Do we assume that there is also going to be some sort of TSA stuff, because that's going to prolong the waiting time and the whole thing?
A TSA element, could there be necessary
and there
to
is
get
also
through security?
Security, the cyber security. So if it's AI fully, then we are subject to a cyber threat.
Now you're above my pay grade, because I'm not.
It's a great question, though.
I'm not sure common sense and that stuff are linked together. If it were me, I would say, and they actually do say this, that really they assess risk by the energy that the vehicle carries, and these vehicles are actually very low energy. And so the risk is much smaller than the risk of a large aircraft. Not to say that they're not going to do something, but that helps mitigate that risk.
Good question. Embry-Riddle students ask the best questions in the world. Over here now for Dr. Anderson.
Hi, I'm Rose Moskowitz. I'm a mechanical engineering freshman here, and I was wondering, there's been a lot of discussion about the commercial use of these with commercial transit systems such as Uber, but I was wondering if you had any insight about the possible application of public transportation, similar to a state-funded bus system, if these systems could be used in that manner.
In other words, replacing the public bus system with something like this.
Well, right now, the way electric propulsion is, and the answer is probably, but it's going to be down the road further. Because the nature of the technology is that it's going to start small. And so starting small really promotes the point-to-point motion instead of the hub and spoke, where you have a bigger vehicle flying to a hub. And so just the nature of how the technology is going to mature, I think, is going to stand up in more of the Uber model before it stands up in more of the public transportation model. But I think that's probably down the road. I think you're looking at vehicles that are 10 to 15 seats that makes that a reality, going to more concentrated locations. And I think as battery technology and hybrid technology advances, you may see that.
Thank you. Over here, your question.
My question is sort of connected to that. I'm Evan Maduro, I'm a sophomore. Last year, I actually went to the EAA convention in Oshkosh, and I got the chance to see, well, I wish I got the chance to see one of these concepts fly.
Workhorse.
Yes. they couldn't really get it off the ground in sort of breezy conditions. So, well,
Remember when I told you about the fixed rotors?
yeah, so
They have fixed rotors.
I was wondering, like with these very like light aircraft, like us engineers like to make them in the air. Do you think they'll scale up to more like buses or stay at the size of competing with cars and SUVs?
Well, they're certainly going to grow, but again, the technology is going to start off small because the energy required to do this really doesn't lend itself to batteries right now. Now, Workhorse is a giant octocopter, which is to say that it's got fixed pitch blades, and they should have looked at Augustine's thesis before they made that vehicle, because they're on the bad side of that curve, and they can't control their attitude anymore because the motor can't spin the props in delta torque fast enough, and they ended up on a windy day in Oshkosh, and exactly what you said happened. And it's really funny because I gave this conversation at the EA chapter in Spruce Creek, and one of my friends, who I'll leave nameless, I went through all this, and he came up after it, and he said, well, that's not true. And this is a very easygoing guy that I talk to all the time, and he got very irritated. He said, you're not correct on that. And I said, well, I am. We've done a couple of master's theses in this area. And what I came to find out later on is he invested $1 million in Workhorse. And the problem is that Workhorse had a subscale flying version that looked pretty good. And when it got a little bit bigger, guess what? That scaling law caught them, and there's no way around it without going to helicopter rotors. And they don't know how to do helicopter rotors. They just know how to do octocopter, DJI type stuff. The good news in the position that you're in is that this can't be done in a garage. And so we're going to need skilled engineers that can work very complex problems, because this is not going to be a trivial aircraft. It's going to be a complicated aircraft.
We have time for 2 more questions over here. You're next with Dr. Anderson.
Sure. My name is Michael Hadger. I'm a sophomore studying aerospace engineering, and you had talked about the automated traffic management and spacing. What does this look like in a city that's like really close to an airport such as like Boston, where I'm from? The city, like the downtown area, is really close proximity to the international airport there.
Yeah, I think when this type of technology is finally deployed, which is probably a ways off, it'll be a lot easier to have vehicles operate in much closer quarters, because there's going to be peer-to-peer, basically, looking at ADS-B, which is, the onboard GPS, communicating with other vehicles and using artificial intelligence to sequence vehicles and look in 4D trajectories, so what's going to play out in time as these vehicles move around. And I think actually this technology is going to allow us to get much closer together and still maintain the safety aspects that we expect today.
Thank you.
Thank you. And our final question from our audience.
My name is Benjamin Bachmeier. I'm a first-year PhD student in Dynamics and Controls in Aerospace Engineering here at Riddle. My question combines the engineering point of view and the business point of view. So you talked about the large amount of companies which have grown in the last couple of years, like really dozens or even 100 companies worldwide which are really trying to work on this. How do you think many of those small companies can develop an edge on big companies like Boeing and Airbus, who have large workforce, large budget, and also a lot of experience?
Large bureaucracy.
Yeah, maybe. I don't know. So, yeah, what are chances from the engineering perspective to develop kind of an edge on large companies, and how do you think how many will survive in the end?
Well, I'll take the last part first, which is that I think there's about 6 companies that make single-engine airplanes nowadays. Back in the 1920s, there was hundreds of companies. And so we're going to see that. We're going to see that there's this great expansion and then a combination of the companies that are successful, and then mergers and acquisitions down to a narrow line of these. But that's going to take 20 years to play out. I think there is room for creative thinking in here. And I don't think Boeing has a patent on that. Obviously, they have a lot of resources to their disposal. But I've seen many companies that have ideas that are beyond what Boeing is pitching. And Boeing is probably a little bit risk adverse, and this is a really out there sort of thing. So if you're willing to move fast and you have good ideas, I think you might have an edge over that bureaucracy, which is a little bit cautious in its nature in moving about in new technologies.
Thank you. Before we part tonight, we want to remind you about the next event in the Embry-Riddle Speaker Series. It will be on March the 4th. We'll be talking about cybersecurity and transportation. We'll have a panel dedicated to that, and we'll take your questions. It'll be at 7 o'clock. The doors open at 6, Monday night, right here, the campus of Embry-Riddle. I want to thank a few people: Natalie Hong, Nell Azencott, Carrie Dement, Carol Fuller, Daryl Labello, who shot the video tonight, Tony Petro up in control, Dr. Jeff Kane. It's always a pleasure to work with you, Dr. Kane, as well as Dr. Maj Mermurani. Thank you for this great opportunity. To Provost Dr. Lon Muller, thank you for your support in all of this. And our special guest tonight, the speaker, Dr. Pat Anderson, ladies and gentlemen. Wonderful presentation. Thank you, Doctor. Have yourself a very pleasant evening. We'll see you on March 4th.